So basically what we're going to talk about today is TSN, time-sensitive networking, which is not a single standard. TSN consists of multiple standards and extensions and profiles, as Nikos already mentioned before. It evolved from the AVB task group in 2012. The AVB task group was focusing on latency-free delivery of audio and video data, and from that task group, the TSN task group separated. So as mentioned before, TSN is not a single standard. It's more or less a collection of substandards and extensions, which are focusing on network-wide time synchronization, as well as determinism in data transport, as well as low latency and low jitter. So, and as TSN is working on top of the classic Ethernet standards, it scales with the speed and with the evolution of Ethernet. So what's the vision behind TSN? So one of the visions is that TSN, time-sensitive networking, is enabling the merge between IT and operational technology. It can avoid the use of proprietary and incompatible solutions like widely used field buses, and it is focusing on interoperability and scalability of networks. So I just listed some of the standards in this slide. So as you can see, one can cluster the standards a bit. So some standards like the 802.1 AS and its profile IEEE 1588 focus on time synchronization, which can be seen as kind of a basement for the TSN standards. So often TSN applications make use of time synchronization. Another cluster is the standards focusing on bounded low latency, focusing on reliability. And on top of these standards, there are additions focusing on resources and API, searching for solutions for configuring networks and so on. So, and to ease a bit the use of TSN, recently there is a strong push for the definition of profiles, of TSN profiles, focusing, for example, on audio-video bridging, front-haul application, or industrial automation, automotive communication, and the latest of these profiles is now aiming for airborne use of TSN. So with that being said, I want to step through some of the most important TSN standards used nowadays just to get everyone on the same level of understanding before we start deep diving on the latency topic for today. So as already mentioned, most TSN applications make use of the time synchronization according to 802.1 AS or its revision AS 2020. So the time synchronization is focusing on network-wide operation. It's aiming for network-wide time synchronization. And if the AS standard is used as required by the standard, non-AS capable devices would break up the network. So there are some ways of dealing with this drawback, but I will keep them aside for today. So the synchronization, the network-wide time synchronizations usually is started by periodic announced messages, and then a grandmaster select algorithm called BMCA would select the device with the best accuracy in regards of clock precision. And this device from there on will serve as a grandmaster for the network. And all the slave devices would synchronize to the grandmaster clock provided. So once a synchronization was established, periodic synchronization and follow-up frames will keep the synchronization up and apply corrections to the synchronization where needed. The AS standard is based on a peer-to-peer measurement of path delays. So it can be seen of like measuring the delays packet need to be transported between two communication partners, and based on this information, the whole synchronization of the network is set up. Then there are standards for shaping traffic in terms of bandwidth allocation or traffic timing. So first of all, to mention here is the 802.1 QAV, the so-called credit-based shaper, which was already used by the AVB task group back then. It is operating in a credit-based way, which means each data stream would have its own credit, which is decreasing by sending frames and increasing in times when there's no traffic being sent. So, and if a data stream would have negative credit applied, it would not be allowed to send traffic for that period of time. So this gives you the opportunity to set up bandwidth per stream in the network. The next shaper, which can be seen on top of the AS time synchronization, which is making use of QBV AS time synchronization, is the 802.1 QBV time aware shaper. So the basic idea behind that is to make use of the network-wide time synchronization and to define repeating cycles within on the timeline. And there one can define a number of gate operations where one would open the gates for certain traffic classes and block the channel for others. So with that, you can reliably define time slots when different streams might send data on a channel. Another standard I just want to briefly mention here is the frame preemption, which is a mix of two standards actually. It's focusing on extreme low latency data transport for chosen traffic classes, which we call express traffic. So how does it work? In the image on the left side, you can see a data transport without frame preemption enabled. So if a low priority packet is already on the line and there would be express traffic showing up, the usual way is that the low priority data frame would be transferred, and afterwards the express frames would be transferred, which gives you a huge amount of latency in the worst case situation. If you switch on the frame preemption, this would allow express traffic to interfere the data transport of low priority background traffic, and which would result in fragmenting the low priority background traffic with the benefit of ultra low latency processing of express frames. Another standard I want to briefly mention is the reliability standard 802.1 CB, which is called the frame replication and elimination for redundancy. This standard gives you the opportunity to split data streams and transfer them using separate physical channels and reunite these data streams on the receiver side. The last standard I want to shortly mention here is the QCI, per stream filtering and policing standard, which is giving you the opportunity to, let's say, identify the bubbling idiot in the network, which would enable the possibility on checking if certain traffic is currently allowed to be sent. So you would set up using this stream this standard gates where traffic can only pass in certain frames of time, and if they don't, they will get terminated and an error would get raised. So about TSN cast and Fraunhofer IPMS. So there are several TSN enabled IP cores which we offer. So first to mention, there's the TSN endpoint core, which is basically used as a network endpoint with TSN capability. And the next on the list is the TSN switched endpoint, which is enabling daisy chain applications or even ring topology, also the like. The more complex solution, the TSN switch, can be seen over here, which is an infrastructure component, which is a TSN enabled switch IP core with optional host port functionality. And then we also offer a CAN to TSN gateway, which is enabling bridging between TSN and CAN networks. So all these IP cores have extensive standard support for TSN standards. They are target independent, which means they can be used for FPGA designs for any FPGA vendors, or they can be used for ASIC implementations as well. We focused during development on small footprint and cut through and store and forward possibility. All these cores offer high synchronization accuracy based on 802.1 AS. They come with extensive software support, and they support stream-based data handling as well as packet-based data handling. They hereby be used with CPUs. And what we optimize these core for is very low and configurable forward latency.